Okay, that's the formal definition of a derivative. So what's the difference between the formal definition of the derivative and what we've already done before? What's the only difference? Yep, so you aren't going to see me using a anymore. We're just going to use x. We may use a in notation, but for all of our problems, we'll be using x. And really the idea is this. If you have a function and you take the derivative, the result is a function as well. Okay? And so now we have all sorts of operators that imply derivative. You guys are used to this operator right now, f prime of x. Okay? So if you see prime, that means take the derivative. If you see y prime, that means take the derivative. If you see dy over dx, that's nice because it actually states the dependent variable and the independent variable. So derivative of y with respect to x. You may see derivative with respect to x. If you don't have a variable named, you might see this. Derivative with respect to x. I don't really use many of these other than the first two. You'll see me use this quite often and this one quite often. Every once in a while I'll use this one. And maybe once in a blue moon I'll use this one. I'll never use that one. So, but your books will use some of these. And you should be used to them. Okay? All right? Any questions on that? Okay, flip it over. It says, use the graph of f of x to the right to make a table of values for f prime of x. Then sketch a graph of f prime of x. So what I want to do is I want to create a graph for f prime of x. This is f of x. And in order to do so, I'm going to create a table of values. Okay? So there are some very, very important slopes out here that I can point out. For example, if you look at 1, 2, 3, 4, negative 4 right here, can you tell what the slope is at negative 4? Sure, very negative, okay? Negative 6, negative 8, negative 10, something like that. But it's hard to come up with a real solid value, isn't there? Is there an x value where you know the slope of the function? Negative 3, okay? What is the slope at negative 3? 0. What's another spot you know the slope? 0. And the slope is 0. All right? Now you may even say, that might be enough for you to be able to sketch a graph. You might be like, okay, I don't know. However, if you want to look at, say, the slope at negative 1, what would you approximate the slope to be at negative 1? 1. And the slope at positive 1 appears to be about negative 1. So if you look, when we plot some of these values, negative 3, 0, 0, 0, 2, 0, negative 1, 1, 1, negative 1. And at negative 4, will I have a positive value or a negative value? Negative. In fact, it would be very negative. At positive 3, will I have a positive value or a negative value? Positive. You can see the slope is very positive there at positive 3. So you can see I'm going to have this kind of a shape. Now, there's a certain prediction that we want to make about these shapes. All right. Number 1, what degree is this equation right here? What degree? 4th degree. This is a 4th degree equation. What degree is this? 3rd. When you take the derivative, you will see the power decreased by 1. All right? You're going to see that happen. Second of all, is this a positive x to the 4th or a negative x to the 4th? It is a positive x to the fourth. Is this a positive x to the third or a negative? Positive. If it's a just because cubics, when they're positive, that's what they look like. If it was negative, it would look like that. Okay? So if it's positive, then the resulting derivative will be positive. Okay? If it's negative, the resulting derivative will be a negative graph. So we can make some conjectures about this. Also, as we said, the degree will decrease by 1. Okay? So that should be able to give us some hints as to how to sketch these things. So part of your test will be, can you identify, given the graph, what the resulting derivative would look like. So I have a worksheet for you. I'm going to have you guys work on right now. Let's get practice this, and we'll get back to the rest of the lesson. I'm going to pause this. Please do not. Okay, I gave you some good time to work on that. But yeah, you'll finish that off. That'll be an assignment. And I won't give you another assignment on top of that. I just want to show you to be able to do some of the problems on the backside. So in order for a function to be differentiable at point A, a couple things have to be accounted for. Number one, f of A must exist. Okay? It has to be continuous. Second of all, the limit as h approaches 0 from the positive of f of a plus h minus f of a all over h must be equal to the limit as h approaches 0 from the negative of f of a plus h minus f of a all over h. What's that? That's what I have right there. This is different. This is the derivative from the right equals derivative from left. Okay. Derivative from the right is equal to the derivative from the left. Now, that's what has to happen in order for a function to be differentiable. So as soon as I give you some examples like, oh, well, yeah, we know how to do these, there's always examples that are trickier, and they don't always make sense. So here's 3 classic examples of where a function is not differentiable. The number one would be a corner. Anytime you have a corner or an endpoint, that causes issue and concern. So this graph right here, I'm going to sketch a graph that has a corner on it. Okay, so this is an absolute value function. And I'm going to sketch its derivative right below, f prime of x on a set of axes. Okay. Now my question 2, that absolute value graph, is it continuous? Yes, it is. But let's check the derivative from the left and the derivative from the right. If you look at the left side of this graph, and I mean left from -3 on over to the left, what is the slope of that line? -1. Let's look at the right. What's the slope of the line here? +1. So you can see that the derivative exists here. It's -1. The derivative exists here. It's -1. Derivative exists here. It's -1. But the derivative does not exist at -3 because when you check from the left and the right, they're different. Slope is -1, slope is +1. And the reason why that should make sense to you is if you try to draw a tangent line, a lot of people would draw the tangent line like that. Well, no, that's nonsense. Because I could have just as easily drawn a line that went through the point once, like that. Or this one goes through it once. So which one is truly the tangent line? It technically does not have a tangent line at that point that we consider to be the derivative, okay? Because you have all sorts of different slopes that can match up. So that doesn't work. You got problems. So what would the derivative look like? Well, this function is continuous everywhere, but its derivative is not continuous everywhere. There's no derivative at -3. So this graph cannot have a value at -3. Let's sketch the graph. 1, 2, 3, 1, what is the slope before negative 3? So from the left. Negative 1. And it's always negative 1, correct? So I'm going to have a line that has a value of negative 1. I'm going to put an open circle at 3, or negative 3. After negative 3, okay, to the right, what's the slope? Positive 1. So you can see that I have that. So that is the derivative graph of that function. You can see, is this function continuous or discontinuous? Discontinuous at what value? Negative 3. That's because its graph is not differentiable at negative 3. See how they match up? So you should always be able to pair up the graphs and understand which is which derivative. Let's look at another example where it's discontinuous. I'm sorry, not differentiable. And that's when you have discontinuity. So I'm going to draw a graph that will be discontinuous. You can sketch the same one. You got it? Okay. So the derivative does not exist at what points on this graph? Negative 3 and 3. Okay, because the derivative is different from the left and the right, and it's discontinuous. You cannot have derivatives at endpoints. You can have derivatives from the left. You can have derivatives from the right, but you cannot have a derivative exactly at an endpoint. Okay, so let's check this out. What is the derivative of this part of the graph? What is the slope? 0. So I have a horizontal line at 0, all the way over to negative 3. Can you take the derivative at negative 3? No. So you have an open circle at negative 3, and it has a value of 0 everywhere behind there. Let's look past that. From negative 3 to positive 3, what is the slope? Positive 1. Can you have a derivative at an endpoint? No. So I will have open circle. That. So that's a graph of the derivative. And then from 3 on is a little bit confusing, but I think we can handle it. What is the slope right at the top up here? Yeah, like negative infinity. Yeah, it's, it's very, very negative, okay? How about the slope, like, say, right in the middle here? Negative 1. How about the slope as you get out here? Close to 0, right? But it's still negative. I'll call it negative 0. That's a ridiculous idea, negative 0, but it's just to this side of the x-axis, isn't it? Okay. So I'm going to draw a value that's really, really steep at the bottom, or I'm sorry, very far down, and then a value at about negative 1, and then a value just below 0 as it goes out. And you can see that I'm going to end up with that kind of a graph. Now, this will confuse some people, and I just want to be careful as we watch here. Some people say, well, you just drew a graph with a positive slope, and it was supposed to be negative. Well, can you tell me what I said that's incorrect there? It's okay that the slope is positive. It doesn't matter that it's positive. What matters is does this function have a positive or negative value right here? It has a negative value. The derivative is the slope here is negative. That doesn't mean that the slope here is going to be negative. So it could be positive or negative. Just depends on the nature of the graph. Okay. The fact is it has negative values. It's below the x-axis. That's what we want. And then we have a final graph, and this is definitely the most difficult for people to recognize and analyze, and that would be the graph of, I'll give one example. This is a classic example. F of x is equal to x to the 1/3 power. We would call this a vertical tangent. And the graph looks like this. Is that really it? Okay, really quick, let me finish this off. Okay, vertical tangent. So, if you were to sketch this graph, watch what happens. Okay, slope here, positive or negative? Yeah, it's positive, but it's really close to 0, isn't it? So we'd have a positive value, close to 0. How about here? Positive, negative, but close. It's positive. It's going up, but close to 0. Okay, so that's what I have. Now, look at right here. As I get close, okay, is this slope positive or negative? And it's getting very, very positive, to the point where you would have a vertical line. What's the slope of a vertical line? Undefined. So you get, as you get closer here, the slope gets increasingly large. How about after you pass 0? The slope is still extremely large. Okay? Yes, it's decreasing as it goes, but the slope is still positive. As we talk about slope of lines decreasing, then we're talking about second derivatives. We'll get to that later. So that would be that graph. Please try to finish off the back side. And tomorrow I will show you some good stuff. Wednesday or Thursday, I will show you the shortcut to finding derivatives.